Go.
You can scan the sample from size like this big to like this big. So depending on the size of your sample, your resolution also changes. If you want to scan like very high resolution, like 3 micron, which is the limit of this machine, then your sample will be pretty small. So this machine you can basically just put a sample on the stage and the X-ray shoot into a sample, and the reflected image get collected in the panel, and you import this data to this computer, and you can reconstruct the radiograph to make it to be 3D CT images. So
what is the highest resolution that we can get with this?
The highest resolution depends on the size of the focal spots, which is 3 micron for this machine. So you cannot go higher than 3 micron for this one. Yeah.
Where is the sample?
So
you guys can go near and look at the stage as well.
yeah,
as the
so
stage.
you can put a sample over here, depend on like what kind of sample you have. You can design your specific holder to put on the stage. And you can also use different filter like copper to filter a certain spectrum of the X-ray to get better images. Yeah.
What is the typical size of the
The typical size of sample. So if you want to scan like 3 micron, your sample should be like this close to the gun. So this is the gun. If you want to scan like 50 micron, then the sample could be can be this big.
All right.
So it depends on the size of the sample. I can show you some images I've uploaded to the digital portal. So this is like a hybrid bearing sand sample. So what you see here is a sand pack saturated with so sand is the black granular shade. The hydrate which is using xenon to form hydrate. The xenon hydrate is these white pixels, and what do you see else for the green blocks of the xenon gas. So if you click one image and go to the very end, this one doesn't have. You can have like two ways to do it. So one is during the scan, it can reconstruct using the software over here, but it can only export like a single volume file, which can only be read by like some commercial software like volume graphics or a visual. But if you wanted to export as an image stack of tip images, you need to import the data from here and create tip image stacks. But yeah, it's pretty supported.
And can we do fluid experiments inside this scanner?
Right now, you can only design like a lab-made flow apparatus to actually what Jasper did, because we cannot run lines through the scanner. So you have to have remote control pump to inject fluid inside your sample.
How long does each scan take?
So it depends on the how many frames you are taking at each projection angle and how many projections you are taking. So ideally, if you have more projections in the 360 degrees, you have better quality image. So for instance, at an exposure time of 250 milliseconds, and you go 3,000 projections, and at each projection you take 4 frames as an average, that takes 15 minutes. So for most of my scan, it takes from an hour to 10 minutes.
So for any fluid experiments, you don't get the real-time data.
No, yeah, you cannot achieve that using the microCT unless you inject very slowly. Yeah. But you can actually do these 2D radiograph like what Jasper did. So you take radiographs at very small intervals. So you can actually record how the saturation of your sample is changing over time. That's pretty much like CT, medical CT, right? So for microCT, you are projecting as a single radiograph, and you are reconstructing many single radiographs for the whole samples at different projection angles. X-ray CT. So typical X-ray CT, the gantry is in the vertical direction, so the people can lie down on the bench and go inside and get these scans. So, but this one, you can actually rotate the gantry in the horizontal direction as you see it right now, and you can put your core holder on that hanging device, and this is a little vertical positioning system. You can lower down your core holder and put just inside this gantry to be scanned during your core flood experiments. So the typical energy for this medical CT machine, it runs from 80 kV to up to 140 kV. And the resolution is different from the microCT. So for microCT, you can go from for that machine, from 3 microns all the way to like 70 microns cubed. But for this one, your resolution is roughly 200 micron square times the depth of each slice. So the slice can vary from 1 millimeter to 1 centimeter. Just depends how many scans you want to get. So basically, you cannot get the pore scale resolution, but you can actually scan the core holder of your sample during the flow, so you can get in situ saturation. So that's the advantage of this one.
Is this machine capable of obtaining the same resolution as the other one, and at the same time having like real-time experiments? Or?
So as I just said, the resolution for this one is sort of coarser. So imagine you have like 200 micron times 200 micron times 1 centimeter. Then you have like thousands of grains inside. So what you get is you actually have like a mix of grains and your pore space, including oil, water, and gas. So what you have to do to get saturation is you pre-scan your sample when it is dry, and you also scan it when it's saturated with your
fluids.
Yeah, fluids. Then you get sort of interpolation if you want to do two-phase core floods. But in case you want to do 3-phase core floods, you actually need to do dual energy scan. So that means you need to scan 2 different energies in order to get saturation of 3 different phases. Because right now you have 2 unknowns, then you need 2 equations to solve it. So, but for the microCT, it's different. As long your sample, your target phases have very different X-ray attenuations, you can differentiate them in a single CT scan. Let's say you have oil, you have gas, and you have grain. Then you can easily differentiate these 3 phases using just 1 scan. Yeah.
So what is the advantage of using this scanner over the other one? Like, it has a disadvantage that it has a very bad resolution compared to the other one. What is the advantage?
So the biggest advantage is you can actually get the in situ change of saturation inside the pore inside of core sample, because you can actually run before I lived here, I have a flow apparatus that have transducer over there, and this transducer run.
This one is set up the same
Yeah,
way?
and I have like those pumps. So this pump and transducer run those peak lines connected to the core holder over here. So when I'm doing experiment, I just need to start the injection, then I close the line, go there and scan it. So actually, I have a few papers about how to use this in situ saturation to calculate the unsteady state relative permeability during the core floods. So that's the biggest advantage. You can make some modification to the microCT, but it's definitely much easier to do this in situ core floods using the medical CT. That's the biggest advantage.
What is the longest sample that you can use? This
restriction on the length of the sample?
Yeah, so I think the longest sample you can go is a little above like 2 feet. So previously I have like 2 feet long core holder, and when you lower it down and it's almost on the floor, so you don't want to hit the floor. So that's the limitation. So yeah.
Second question, is there any problem because the interference to the metal casing of the
Yeah. So for both medical and microCT, you need an X-ray compatible or transparent vessel. So typically people use aluminum, or some people use PEEK, which is high pressure plastic. So for all my experiments, I use aluminum. It's like transparent to X-rays, and it's fine to use that. Yeah.
How much does it usually cost for each image? Probably depends, but
I mean, how much time?
how much time and also the money does it cost?
Like in terms of time, so for medical CT, for both medical CT and micro CT, you can specify the exposure time, which is how much time you want to keep the X-ray shooting to your sample. So let's say if you want the exposure time for the one thing I have to say, so the exposure time is typically longer for medical CT than micro CT because you have bigger sample. So let's say if you like specify the exposure time for medical CT to be like 1 second each slice, then if you have like 1 foot long sample and you want to scan like every centimeter, that takes 3 minutes. The cost of the machine, I think, how much it is?
I think 250,000,
Yeah.
something like that, and that's I think about $1 million. The other one.
No, I think it's pretty much the same. For micro city, it's like 200. Yeah, but to build this like structure, I think it costs the same amount of money.
This was the original machine that was the vertical scanner, the medical scanner, and
Yeah.
then Dr. DiCarlo and someone else actually, they built up this whole structure. And the structure that you see on the top, it actually lowers down so that you can vertically measure the changes in the site. And what
What's
the
the
experiment is
benefit of
like.
that over horizontal?
Come again?
Why vertical instead of horizontal? What's the benefit?
Well, when you
It depends on the type of experiment you're trying to run.
Yes.
Sometimes you need to run gravity drainage, then you need vertical.
exactly right,
This is fixed right now, right? And you can't.
No, this can be moved.
you can rotate. You can rotate back to the vertical direction to
They
scan
can
your
run
sample
both?
horizontally.
Right.
Both horizontally and vertically?
Yeah. So you see this like structure. So you have your sample core holder have like a beam, so it can fix here, so it can move. Yeah.
So when it was a medical scanner, there was a bed here, and that's where this is called a couch, and this basically moves in and out.
Yeah.
What they did when they transformed it to a vertical scanner, they translated this motion into vertical motion on that beam. So when you basically move this, that beam moves as well.
Right. So these two, the couch and this vertical position system, they are synchronized. So when you actually moving this vertical positioning system, although this is not being used, but it's also moving correspondingly because they are programmed together.
So the CT number this one outputs is calibrated to water?
Right. So for micro CT scanner, you don't have calibration. You just use different phase have different screen square number. But for this one, it's calibrated using air and a big cylinder of water filled with water. So the CT number of water is 0, and for L is -1000. It is the Hounsfield unit. So.
What form of, how do we get the output? Like, is it an image file or is it
So,
a data file?
what you did is after you scan it, you actually get a PI file. So you need to input the PI file to the Linux machine, and there's some MATLAB codes that can convert this PI file to a MATLAB matrix. Then you can work on the matrix.
And you can transform it into an image as well.
Right. Yeah. Because you have the matrix, you can convert it to teeth, whatever.
How heavy are those?
Huh?
How heavy?
Like, they're not that much.
No.
Like, compared to the medical CT, they are this has a low resolution, the images are not that big.
So how old is this machine?
been here since 2008 when David came here. And during, I think 2 years ago, they completely replaced this because old one is dead.
So basically the room is the same, they changed the whole system.
And all these like walls is filled with lead.
Yeah.
How did they get this through the door?
So this was
There's a door over here, but they are blocked there. So it's a very big machine,
So we're using a lot of electricity.
I guess.
Austrian Electric is very happy.
Yeah, you have there's like USB interface.
So these are different scans that we take. This is the core holder. This is the core.
How many slices?
So for this one, 30 slices. So each slice has a thickness of 10 millimeters. So basically each scan thickness is 10 millimeters, and after each scan it moves 20 millimeters. So it's not a continuous scan for the whole core. It depends on what type of experiment you're running. So as Jasper was telling you guys, that we usually use aluminum as the core holder because it is invisible to the X-rays. Sometimes what happens is that if we have a pressure transducer, we need pressure lines, and they are usually made of stainless steel. And because of that, we can see some discrepancies in the X-rays because they attenuate a lot.
So is this an artifact? It looks like
Yes,
Because of
it's
it-
artifact. Because you are using a stainless steel fitting over here.
so. This is noise
Yeah.
produced by
Yeah.
the
Right, exactly.
Okay.
But the advantage of using the pressure taps is you can actually get the measurement of pressure inside the core to avoid
real
the
time.
entry at capillary antifact.
So for example, this is an even worse
So
example.
is there any way to image process that and remove that noise?
I don't.
Typically, I just do
You
not
people
use
usually
it.
just skip that
Yeah.
slice.
You skip the slide.
Yeah. And one other thing you can actually do before you run experiments, you replace this fitting with some thick fitting, which I did.
But I think if you have a high pressure experiment, that is usually not possible to do.
Actually, it's possible. Yeah,
Is it?
I
What is
tried
the-
a little bit.
What is the pressure rating of that material that you mentioned?
But like the peak, it's really at 5,000 psi at 70 Fahrenheit. But you need
High
to
enough.
have good machining of it.
Right.
So for my like experiments, if I just use a plug, it can very well to seal it. But if I actually want to drill a hole through the plug and get some fitting on it, it causes problems. So yeah, but I think it's possible.
Is there any specialized machine shop here in UT to do those?
I did that with Dara.
Okay.
Yeah.
There is a machine shop inside
Yeah.
our department. So the part that's hanging here, this is the core holder. The core goes inside this, the blue part. So this is the core holder.
That's the core I was using.
That's a full core diameter?
It's like a 3-inch diameter. The length is 2 feet.
I think this is the biggest one that we have.
Yeah, that's the one.
There are other sizes, right?
Yeah. You basically there are multiple, like most of the people that run their experiments, they design their work. There's another one here, the smaller one, on the table. So this is smaller than that. So basically you can modify it and basically get a smaller one for you based on your needs. But I think there is a maximum weight limit on the machine. The vertical positioning system, it can handle a maximum weight. So as long as we don't go above that, that's all.
That's for only right?
That is one constraint and the length is another constraint. So that you might hit the bottom part.
Right. And that one is almost hitting the bottom.
Right.
So one was working that is only like this much distance to the bottom.
Plus, if we have a very big diameter core, we don't see good resolution inside the image, inside like in the middle of the core. So we try to have as thin as possible,
Right,
something that we can work with.
So you pretty much want your X-ray to be attenuate and your sample. So you want the size to be small.
I was saying that the source is very important. I mean, from where exactly the X-rays are entering. So if it is rotating, then is there like a circular source, or how do you consider the source?
What's your question? I don't quite understand.
What is exactly the source from which the X-rays are entering the image? Is it vertically? Is it rotated?
So,
the
like,
circumference?
when you see the gantry is like a ring over there, so it's shooting from one direction and collecting from the other direction, and it's also rotating like 300 degree, and then it reconstructs.
So half circle shoots the beam, and the other half receives it.
Yeah.
Basically.
It's not like a half circle. It's like only part of the half circle.
Okay, got it.
Yeah. But it's like keep rotating.
But the receiver is the whole like the whole half circle.
Yeah. So I didn't like open the inside, but I believe the inside it has like sort of like a gun and a receiver, and it's rotating like that.
So there's a set and it actually rotates.
Oh,
on
so
the string.
it's not the complete.
Yeah, it's not like there are multiple
So
of them.
like just like takes energy for the microCT, you are actually rotating sample, right? But for this one, you are actually rotating your panel and the
Okay,
source.
got it.
Yeah. But it's the same thing.
And the output is just images, right? You don't get any physical on paper or something like that. Print.
It's all digital at the moment.
Yeah. So for the medical CT, what you get is already reconstructed image. So it's like scanning and then reconstructing. So it's doing at the same time. But for the micro CT, typically what we did is we just scan and take the radiographs, and later on we get the reconstructed CT images in another computer. Yeah.
What is this?
This I think hit the hard drive when it was supposed to be a hard drive this big.
Oh wow.
This is an old system.
Yeah.
It seems.
So other than calibration towards the water and air, and vertical rearrangement of the machine. So what is the difference between the actual medical usage, CT, and this one?
You mean micro and medical, right?
Sorry. So this is also medical. CT,
Yeah, medical, right.
So what is the difference between the actual medical usage CT and the one that we're using?
So firstly,
It's
we
the same
use
thing.
different energy levels. We use very high energy levels, but these
Yeah.
are poisonous for a human, lethal for a human being.
Yeah.
So they use very low energy levels.
Okay.
So like when you are like scanning people, it's like you're scanning a bag of water, right? But when you are scanning those sandstone, it's like scanning twice or like 3 times density. So yeah, as Hassan said, you definitely need to go high energy in order to get the image, get the X-rays through it. Yeah.
You just need to leave the room before you actually.
Yeah, the door has to be closed and we have to leave the room. And the room, as Jasper was telling you guys, it's lined with lead so that the X-rays don't basically exit the room. And there are some
right.
certain safety precautions. So if the door is not closed, the system does not turn on.
Right.
Same with the micro CT. If the door is not closed and there are couple of other keys that need to be turned on, if they're not turned on, the machine does not start. So these are just safety precautions.
And is there any like residual radiation after using the machine? You have to wait for some time before entering again.
Not that I know of,
No.
actually.
Yeah. I don't know.
Like based on the safety protocol that we've been told, I guess there's nothing. You can just enter
Well, like
right after
definitely
the
need to
scan.
look at the camera to make sure nobody is inside when you're scanning. Yeah.
Well, it seems that one of the cameras not working.
But you think, right, they would have to still be circling the room, right, bouncing off the
Yeah,
walls,
yeah.
except the walls are lead, so it's not going to bounce off the walls, it's going to get absorbed.
Okay.
So not so much will scatter off lead, actually nothing. So that's why lead is used as a, right?
Yeah.
Or that's the hope.
That's the hope.
That is seriously the hope.
Now, that said, I don't see, for instance, here, I don't see anybody wearing a little device. And even in that video that we showed in class the other day, there was the guy was actually wearing a little device, which is what radiologists typically do.
Yes.
Because it's cumulative, it stays with you, radiation.
Very fine, man.
Spider-Man.
So they have a little meter on there saying, okay, you need a vacation.
Because the element like is less dense, like for instance, than iron, right? You have smaller mass of these nuclei and right.
More empty spaces.
It's not fully transparent, it's just enough X-ray passes.
Yeah.
So if you need a holder, that's going to be the holder.